Pairs of lines and angles. We're going to be looking at two things in this video. The very first part is just these four terms that we have here, being able to identify those types of lines. The second thing that we're going to be doing is focusing our attention on parallel lines and when we have another line called the transversal crossing through them. A couple of these I would assume that you are already familiar with. Parallel lines are going to be coplanar lines that will never intersect. Okay, so you could have two or more lines here. They're all going to sit in the same plane. That means that they'd be on a flat surface. The way that they extend, they will never intersect each other. Examples of that would be like train tracks, a couple of lines that should never end up really crossing each other. Perpendicular lines are going to be lines that do intersect, so we'll be looking at two at a time here. They would be two lines that intersect to form a right angle. Okay, and again, these will also be coplanar. We don't actually have to state that in the definition because they will just end up being coplanar. All right, the others that you might not be familiar with here are skew lines and coincident lines. Skew lines are going to be two lines that never intersect, but they are non-coplanar. So at first glance, what you see here with never intersecting, that might make you think of parallel lines. However, these will be non-coplanar. An example of this that you might think of would be bridges. Okay, you have a couple of bridges like roads that are crossing over each other. They don't make contact because there's space vertically between them. Coincident lines are going to be lines that are technically the same line. They occupy the same space. Other words, they are the same line. Example one, we're going to identify examples of lines in this picture that fit the definitions we were just talking about. To make things interesting, what I'm going to try and do here is choose examples that just go with CD, okay? Because there's actually tons of different examples that we have in here, and to kind of narrow the scope, let's use CD as a reference here. Let's also talk about coincident lines first. Coincident lines are the exact same thing. So an example of a coincident line to CD is CD. It's the same thing. You could write it backwards, you could call it DC, but there's not really anything interesting about that one. So we're not going to bother writing that one down. All right, parallel lines. CD. To be parallel to CD, the lines need to run in the same direction and they need to be in the same plane. We actually have four segments in here that are parallel to CD. We've got AB, we've got HG, and we also have EF. So we actually have three choices that are right there. AB, you can clearly see that that would be in the same plane because that would be the top surface. EF, the same plane because of the side. But HG, that would also be in the same plane because you could sort of imagine maybe a diagonal. Like if you cut that cube diagonally, you would be able to see that plane. We'll just go ahead and do AB though. CD, that is a line in the picture here. We got line CD, that would be parallel. This is the symbol for parallel, it just looks like parallel lines. That would be parallel to AB, and I'll call that line segment AB since we don't have the full line running through it. All right, perpendicular. Perpendicular to CD needs to make contact with it, has to make contact with it, and needs to meet at a right angle. Because this is a cube, all of the segments are actually meeting at right angles. So anything that makes contact with CD would work. You got BC, you got FC, you got ED, you got AD. All of those would actually work out. All right, so CD, line CD would be perpendicular. That would be our symbol for perpendicular. It looks like perpendicular lines. Line CD is perpendicular to, let's just do this one right here, DA. All right, and last, skew lines. Skew lines are going to be lines that don't intersect, but they are not parallel. They would be non-coplanar. If they were coplanar, then it forces them to be parallel. So we've got CD, we got line CD, and we don't actually have a symbol for skew. We're just going to write line CD is skew with, and we really got to pick out any segment that is not going to make contact with it but is not parallel. So you can't use your three that were parallel. You could go with AH, you could do that. You could do BG, that would be all right. Let's just go ahead and use AH. All right, so line CD is skew with line segment AH. All right, next we're going to talk about transversals. A transversal is a line that intersects two or more other lines in a plane. Okay, in this picture, we have a couple of lines that are drawn here. They appear to be parallel to each other, and then you've got this third line that's crossing those two. Because it crosses these two other lines, we can call it a transversal. Now, a transversal is only really going to be interesting to us when the lines that it's crossing are parallel. Okay, but by definition, these lines don't need to be parallel, and I want to make sure that that's clear at the beginning. These lines, they can go in whatever directions they do. As long as this third one crosses both of them, you get to call it a transversal. Yet, most of our attention is going to go in the direction of when a transversal is crossing parallel lines. All right, so when we talk about this next part here, corresponding angles, alternate interior angles, and alternate exterior angles, these definitions, the way that we identify them, does not need to come from a picture where we have parallel lines. Most of the time it will, but these definitions, the way we identify them, does not have to come from a picture with parallel lines. All right, so an example of corresponding angles would be angle 1 and angle 5. What makes angles corresponding is their location. Within this intersection versus that one, angles 1 and 5 you could describe as being the top left. That means that the top right, 2 and 6, we'll write it this way. Angle 2 and angle 6, those would also be corresponding angles. As well, angle 3 and 7, those would be corresponding, they're the bottom left, and then you've got 4 and 8. Okay, all those are corresponding. All right, alternate interior angles, we actually only have 2 pairs of these in the picture. One of those pairs is going to be 3 and 6, which are located here. All right, so the reason for the name, alternate interior angles. Alternate means that the angles are going to be on opposite sides of the transversal. So 3 is to the left of the transversal, 6 is to the right. That's the alternate part. Interior means that the angles are going to be inside the lines that are being crossed. Okay, so 3 and 6 are on the inside. The 3, the 4, the 5, and the 6, these are all interior angles where the rest are going to be exterior. But 3 and 6 are on opposite sides of the transversal, so they will be alternate interior angles. That means that the other pair of alternate interior angles will be 4 and 5. And alternate exterior angles, pretty much the same idea as what we got going on here, except that they are going to be outside the lines that we have. So we're looking at 1, 2, 7, and 8. 2 and 7 would be an example. They are on different sides of the transversal, but also outside the other lines. So angles 1 and 8 would be the other example of alternate exterior angles. As mentioned before, the transversals are going to be interesting when they are crossing parallel lines. And that's the picture that I had here. These lines are parallel to each other, and I got that transversal. Okay, what I want to do is inductively investigate the comparison of corresponding angles, alternate interior angles, and also alternate exterior angles. So what I'm going to do is take a piece of patty paper, also called tracing paper, and I'm going to trace the top intersection here. All right, I'm going to label the angles. We got 1, we got 2, 3, and 4. Okay, I'm not going to trace the angles that are down here. One of the reasons for that is because when we look at all these pairs, what we're actually doing is building a relationship from the top intersection to the bottom intersection, right? If you look at your pairs, we've got 2 and 6, top and bottom. We've got 4 and 8, top and bottom. We got 4 and 5, top and bottom, and even 1 and 8. That compares the top and the bottom. So I traced the intersection that I have at the top, and I'm going to compare it to what I have at the bottom. Now, if I just slide it directly down, follow that transversal, you're going to notice that we get a perfect match, that all these angles are actually the same size, right? Remember, these lines are running parallel. So the way that they make contact with the transversal is going to be at the same angle. Now, which ones did I actually match when I did this? Matched 1 with 5, 2 with 6, 3 with 7, and 4 with 8. Those are your corresponding angles. So the first thing that we learn is that corresponding angles, when you have parallel lines in a transversal, the corresponding angles will be congruent with each other. All right, so alternate interior angles. Let's see what happens with that. An example was 3 and 6. Okay, so here's angle 3, here's angle 6. Now, if I just slide it down, it doesn't, sit on top of it. But if I rotate this around, we still have that same type of intersection, and these do end up matching. The 3 matches up to the 6. Likewise, what are other ones? Likewise, 4 and 5 are the other alternate interior angles. So we learned that alternate interior angles are congruent. And the same way I had that positioned with it upside down, we get 1 matching 8, 2 matching 7, which is your alternate exterior angles. So a transversal crossing parallel lines is going to give us back all of these as congruent angles. All right, so example 2. Given the measure of angle 1 as 105 degrees, right? So 105 degrees over here, find the other angle measures in numerical order. So we're going to figure out all of these. Well, 105 is 1. So notice that these lines right here, these two, they are going to be parallel because they have these little arrows on it. So those are the markings to indicate that these are running parallel with each other. All right, so if that is true, that means that this intersection, 1, 2, 3, and 4, is all going to match up with 5, 6, 7, and 8. They're all going to be the same size. But doing it in order here, angle 2, that is right next to angle 1. It is a linear pair with angle 1, so it's a supplement. That would make it 75 degrees. Go ahead and add that in there. All right, and then angle 3. 3 over here, that is also a linear pair to 105, but it is also a vertical angle to 2. So that will be 75 degrees. Angle 4 is vertical to 1. That's 105. And all of these, because the lines are parallel, all of these can transfer over as corresponding angles, which means that 5 is 105, 6 is 75, 7 is 105, and 8 is 75. And of course, we only have 2 angle measurements, right? You've got the supplements, and then those supplements match up as vertical angles, and all of that just transfers over to the other intersection. Example 3, we're going to refer to the same figure that we have above here. If the measure of angle 3 is 68 degrees, okay, so that would be one of our acute angles here. If that is 68 degrees, and the measure of angle 8, which is one of our obtuse, if that is equal to 2x plus 4, what is the value of x? All right, well, 3 is an acute angle, 8 is an obtuse angle. Okay, so they're not the same size as each other. But we only have 2 different angle measurements that are in the picture, right? You've got an acute and you've got an obtuse, unless everything is perpendicular and then you get right angles, okay? But in this case, since we have an acute angle and then an obtuse, these two are going to have to add up to 180. You could match it up this way. You could say that 3 is congruent to 7. So if 7 is 68, this has to be the supplement. All right, so what is the supplement? We take 180, subtract 68, and that will leave us with 112. Leaves you with 112. So we can take the expression 2x plus 4, just set that equal to 112. Go ahead and solve. We're going to subtract 4, get 108 is equal to 2x. Divide that by 2, and x is equal to 54.
Wait, what?